Hi everyone. In this video, I'm going to describe an aspect of image enhancement called image contrast stretching. Before I get to that, I'm going to very briefly review some important remote sensing concepts. We've learned that there are 4 resolutions to any given remote sensing dataset. Spatial, which is the size of an image pixel, for example 30 by 30 meters. Spectral, which is the range of wavelengths being captured, which could be the visible, near infrared, or shortwave infrared. Temporal, which is the time it takes for a sensor to revisit the same location, which for example could be 16 days. And the radiometric resolution, which is the level of differentiation of grayscale values, which for example could be an 8-bit image. In order to better understand image enhancement techniques, it's important to have a good foundation of what radiometric resolution is. Put simply, the radiometric resolution of an image is the number of gray levels the sensor capturing the image is able to differentiate between. Let's do a simple made-up example using a band from a Landsat thematic mapper, or TM, scene. Band 1, captured by the Landsat thematic mapper sensor, captures reflectances between 450 and 520 nanometers, which in the visible spectrum we see as blue. All pixels in the image are 30 by 30 meters spatial resolution. Since we're only looking at one band of the Landsat scene, the image shows different levels of gray, from black to white, which can be called a panchromatic image. Remember that the radiometric resolution is how many levels of gray the sensor is able to differentiate. In this case, the radiometric resolution of the image is 8-bit, or 2 to the power of 8. If you plug that into a calculator, you'll see that it comes to 256. That means that the Landsat TM sensor can differentiate between 256 different levels of gray for this made-up example, 0 being the lowest and 255 being the highest. Each pixel in a digital image contains a digital number, or DN, which is the radiometric value of each pixel. For an 8-bit image, 0 is the lowest, which appears black, which you see on the left, and 255 is the highest, which appears white, which you see on the right. If we repeat that example, but this time with a 16-bit image, we can see that there are 65,536 different levels of gray, because 2 to the power of 16 is 65,536. That means that the sensor can differentiate between 65,536 levels of gray, black being DN of 0, and white being a DN of 65,535. That's quite a lot of levels. Okay, so now that we understand the basics of radiometric resolution, let's try with a real-world example. What you see here is a Landsat TM scene over the southern Gulf Islands near Victoria, British Columbia, Canada. The first thing you'll notice is that the image is very dark, making it hard to see many of its features. To improve the visual appearance of this image, we need to apply an image enhancement technique called contrast stretching. The Landsat image has an 8-bit radiometric resolution, which means that the sensor can differentiate between 256 different levels of gray. If we make a histogram of the digital numbers within the image, we can see that the pixels are distributed from a digital number range, or DN range, of 64 to 201. This means that the contents of the image do not range from 0 to 255, but from 64 to 201. This means that the full radiometric range of the 8-bit image, 0 to 255, is not being displayed by the image. In order for us to improve the visibility of the image features, we can manipulate the DN values of the image so that the minimum, 64, and maximum, 201, are stretched out to be 0 and 255. This is known as a linear stretch. If we apply that linear stretch, we see this image, which looks much better and is easier for us to distinguish between features. There are a number of different linear stretches that we can apply. The most common ones are linear percent stretches, such as 1%, 2%, and 5%, which take the original image histogram values and take the percentage from each of the distribution tails. The higher the percentage stretch, the more contrast you see in the resulting image. For example, here's the original unstretched image. Now the linear stretch. Now 1%, now 2%, now 5%. You'll notice that higher percent image stretches can cause the image to be noisy, or that darker and brighter areas within the image can become overexposed. We need to be considerate of that if we are going to conduct analyses on the resulting stretched images.